Hi, my name is Dan Bliss. I'm a professor of electrical engineering at Arizona State University, and I'm the director of the Wireless Information Systems and Computational Architectures Center. So we're going to talk about spectral convergence, and we should start by talking about needs. Of course, everybody wants faster and more flexible communications. We also want to integrate new functionalities. So in addition just to communication, sensing, positioning, navigation, and timing, and lots of other sensing capabilities. Of course, we want lower cost, size, weight, and power. We would like our radios to last forever on a charge, for example. And so we can think about autonomous vehicles as an example where you have multiple RF functions that you want to implement, and it'd be nice to be able to use the same front ends and the same capabilities to do this. So autonomous vehicles and flying cars or urban air mobility, if you like. As I already said, the next generation of communications, and it's going to integrate satellite communications with whatever G we're going to talk about in the future. And for some reason, we seem to be wanting to wire up every device we can find. And I don't know why you want an internet toaster, but clearly there are going to be a lot of internet toasters. New sensing capabilities. One of the things that we work on is actually cardiac radar. So we're trying to measure physiological parameters using small-scale radars. And augmented reality is clearly going to be an incredibly important technology in the future as we overlay external information on what we see in the physical universe. And then for reasons that no one will ever be able to explain to me, I'm sure that fully immersive 3D interactive CAT simulations will be a thing. In any case, so if we start thinking about spectral convergence, what we do is reuse the same RF millimeter wave energy to do multiple things simultaneously. We want to remove those artificial barriers. And there are multiple aspects to that. So one is you want to be able to design your waveforms to achieve multiple functions. You have to have receivers that are able to receive multiple waveforms simultaneously. These might be very different kinds of waveforms, all in the same band at the same time, and you want to be able to disentangle those signals. And then critically is the network resource optimization. If I have this network of nodes, and each node has its own goals and trying to achieve different things, these nodes will work together to achieve some things, and some things these nodes are going to be greedy and want to serve their own needs. And you need to work together with some sort of global resource optimization to make the whole system work well. And fundamentally, we were thinking about trying to improve rather than degrade performance. So we have opportunities by having all these nodes actually operate together. So this is a co-design perspective. So one example is with the progress in 5G, clearly we're trying to integrate millimeter wave into cell phones, that sort of technology. If you have that nice millimeter wave technology integrated in the cell phone, why can't I reuse that for gesture control to improve the machine-human interface? Using the same waveform at the same time. Already mentioned the automotive example, but I have cars that would like to know what's going on the road with other vehicles. So there's a radar component to this. There's also potentially a communications component, and we should probably consider a relative P&T component as well. And then for the Department of Defense, there are plenty of interesting opportunities as well. You have a lot of extremely valuable assets. And every platform is expensive, and if these platforms could do more functions with the same RF resources, clearly there are significant opportunities there. So going after these sorts of approaches, it's required that you have an improved set of tools and efficient, flexible computational systems, and the advances we made in those recently or are making in those. That's enabling technology. And another piece is flexible RF front ends. That's also enabling technology. So I want to talk about processors, which will allow us to do the next generation software-defined systems, RF systems, not just software-defined radios. So historically, for good reasons, if you wanted to implement an expensive sort of communication algorithm, then if you're going to really want to make that efficient, you're going to have to go to a full custom ASIC. And so you see in the plot in the upper right, you have a lot of operations per second per watt if you go to full custom. But if you want to program something and make it easy to program, then you want something which is like a scalar processor. like the kind of processor that is in your laptop, there are more than 2.5 orders of magnitude difference in performance in terms of giga operations per second per watt. And you see that's fairly invariant even as the node technology has moved over time. So what you would like is the best of both worlds, but of course it's easy to ask for things. There are reasons why we think you can actually get both improved programmability and improved performance if you're willing to constrain your set of problems. If you take a look at the typical RF class signal processing problem, there are typically a small number of tasks which are actually dominating the computational consumption. And if we accelerate those particular tasks, then we can actually do a much better job of executing a reasonably flexible set of programs or applications while still maintaining an extremely high efficiency. The problem with heterogeneous processors, which is the solution, core-scale heterogeneous processor, which is the solution that I'm suggesting, is that they're very difficult to program. That is, you have to carefully thread the processing going through these accelerators. And that's a very high burden, which means now I've just ruined one of my goals. So one of the things we've been working on is actually providing all the software support and intelligence that will allow a more automated approach for the programming of this. And we are working on this processor. The other thing is the novel flexible front ends. So as the environment changes, as the requirements change, as the density of nodes change, all these things move around, you would like to be able to match what you're doing to the environment and to the requirements. And what's been really amazing over the last couple of decades is the significant improvement in flexible front ends. So there was a sea change, I think, for all of us who worked in the area when the 9361 came out, and the family of front ends that are related to it. Suddenly, what was a large design project just to get a flexible front end to work with your radio suddenly became easy. You would just go buy the chip and go do stuff. A huge difference. And now what we're seeing is that there are additional advances that are occurring. This is maybe not quite so recent as the polyphase mixer, the idea that instead of using a traditional sort of single phase mixing, that you would do a polyphase mixing. This allows you to have more flexibility in terms of interference mitigation. And then there are more aggressive approaches as well. DARPA's RF FPGA approach is an example that would allow you to have essentially a programmable front end. Now, that's more speculative at the moment, but clearly we are moving in that direction of having very, very flexible front ends. So putting these things together, we can start thinking about applications that are really far more aggressive. So one example that I'm just showing here is the automotive problem. So what I like to do is simultaneously do joint communications, radar, and PNT. That's positioning, navigation, and timing. So I have a little cartoon scenario. In the cartoon scenario, what you see is you see 4 automobiles. There's one legacy automobile which basically is not talking to the other automobiles, so it can't announce its presence. But automobile number 1 has a clear view of the legacy automobile. It also is using the same RF energy, can potentially do very good exchange of timing with automobile number 2. So it has PNT, relative PNT with respect to automobile number 2, which turns out is better than the radar, and also is talking to it. And then automobile number 2 can then communicate with automobile number 3, and thus automobile number 3 can be informed of the position of the legacy automobile as it's crossing the intersection, even though there's no line of sight path to actually communicate the signal. And potentially, because this is a high bandwidth signal, this can be done very quickly. So we can convey a fair amount of information very quickly. We're reusing the waveforms as we go along, and we can think about how to process that. So we set up a sort of a simple analysis with what are reasonable, although not exactly the parameters that are commonly used for automotive radar, sitting at 77 gigahertz. We played a little bit with knowing that chips are everybody's favorite approach for radars, and we didn't want to fundamentally change that. So what we've done actually is played with the exchange of information by using chip pulse position modulation. And in addition, we also have varied the parameters that are associated with a couple of the different the radars, such that we can move between how much bandwidth is associated with one user versus the other user. So when you do that, you can actually determine a performance manifold. And so the three axes you see here are the P&T standard deviation, the radar standard deviation, and the communications rate. And that's the P&T is between car number 1 and number 2. The radar is between car number 1 and the legacy vehicle, and the communication is between car number 2 and car number 3. And depending on the needs of the situation, you can move along this manifold by just changing the underlying parameters of the system. In this case, the split of the bandwidth between the two radars. In general, for a more complicated system, there will be some much higher dimensional space with these parameters that you can't visualize. But here, at least, it's convenient. You can see that manifold, and as I said, you can easily move along that manifold by just changing some parameters depending on the needs of the situation. All right, so path forward. We're just encouraging breaking traditional sideload sensibilities, and we can do that given the advances of current technologies that are happening now. And we can incorporate multiple simultaneous functions within the same system. All our favorite things like communications radar and P&T, but lots of other things too, and new cool stuff that hasn't even occurred to us yet. Thank you very much.